welcome to my third session on three-phase AC circuits in our journey together in the fundamentals of electrical circuits. I still maintain that I repeat the refrain rather, that AC is still very easy. And when you're talking about three-phase AC circuits, then it is more or less an extension. So let's look at some of the problems here. Though we have been talking about phasors generally with respect to vector diagram, etc., I just named this session as, and it's the last session in three-phase AC, that phasor-related problems, because I'll be looking at a few single-phase AC circuits as well. Okay, so moving on to the first problem, the phasor diagram is also there in this case, but it is a repeat of a similar kind of question, wherein we have a three-phase system with a resistor, an inductor, and a capacitor connected in star, and the neutral wire is also there in this case. And what is given is that a three-phase load is connected to a three-phase balance supply. As usual, the supply is considered to be balanced. And if voltage VAN is equal to 100 angle 0, VBN is equal to 100 angle minus 120, which means that this is a this follows the phase sequence of ABC, okay, or R by P, or 1, 2, 3, okay. And VCN is equal to 100 degree, 100 okay, so I don't know what we call it, 100 angle minus 240 degrees, okay. Angles are considered positive in the anti-clockwise direction. This is the case for electrical quantities, okay. The value of R for zero current in the neutral wire, okay. So what all do we need to consider, okay. So we can of course compute all the currents and then set the neutral current as equal to 0, or else we can just use common sense. What does common sense tell us? It tells us that there is a balance supply and the impedances are a little balanced in the sense that we have minus J10 as the capacitor reactance and J10 as the inductive reactance. So they have the same magnitude and an angle difference of either plus 90 or minus 90. So the vector diagram might help us be more intuitive and do the problems in a very simple manner. So what do we have here? VAN, VB and VCN exactly as given. And then we see that since the source is now phase to neutral, it's very easy to see that each of these phases will be drawing current. Okay. So what is phase B doing? Phase B is drawing a current as given by VBN divided by J10. Or in other words, there is an angle. There's 90 degrees on the denominator, or what may be called as a reduction of angle, or minus 90 degrees added to whatever is shown as VBM. So that's the reason why IB is given as equal to 100 angle minus 120 by 10 angle 90, which gives rise to 100 angle minus 210. Okay, so it can be minus 210, which means that it will go into the second quadrant. Okay, if you or else it's the same as equal to 1 plus 150, in which case also it will rest in the second quadrant. Okay, and similarly, IC is also very similar. It can be seen that it is equal to 100 angle minus 100 angle plus 120 divided by 10 angle minus 90, okay, because it is minus J10. Okay, so now this minus 90 will come to the numerator, and if you call it as so, and then it becomes minus 150 degrees. Okay, it's all the same as equal to plus 210 degrees. Okay, so you because it is plus 120 and plus 90, it is equal to 210. So you can call it as equal to it is still going to the third quadrant. So now we have these two currents both in the second and third quadrant and of equal magnitude, such that their imaginary values cancel. So it's only the real quantity which has to be cancelled by the current carried in the through phase A. Okay, so what is it equal to? It's equal to the sum of the two currents, because it's in the negative direction. So if you have a positive direction, it will be the same. That's the reason why we see that now our IA or minus IA is the same as equal to minus 210. It is the same as equal to as was mentioned earlier, whatever is taken to. So we take only the horizontal component. So when you take the horizontal component, it becomes 10 into root 3 by 2, because it's the projection on the horizontal axis, which is cos 30, which is root 3 by 2. Okay, and there are two of them. Okay, and so together it becomes equal to 10 root 3. And then, so 10 root 3 is the current. So now we need to find out the resistance. How do you find out the resistance? By simply dividing the corresponding voltage by the resistance, which is 100 divided by 10 root 3, which is equal to 5.77. So it's a simple problem, and we use the Phasor concept. Okay. So moving on to the next problem, where we are having, seemingly it's a three-phase question again, and the voltages are 230 RMS values again, and it looks like okay. Let's see how the construction goes. Okay, so 230 angle 0, 230 angle minus 120, 230 angle minus 120, and thus neutral as well. Okay, and if you look at the first wire, okay, first coil around the transformer core, it looks like a transformer core. We are seeing that, okay, we need to find out the directional sense. Okay, so the coil is going behind, okay, and then emerging to the front. Okay, so normally you take your right hand and place your hands such that it follows the current. Okay, so if it follows the current, we can see that the flux is directed downward as far as coil A is concerned. Moving on to coil B, it can be seen that the coil is moving to the front of the core and then going backwards. If you hold your right hand in the direction of the current coil, and in the direction of the current that is supposed to flow through the coil, you can see that the flux is moving upward. Okay, the flux is upward. Okay. Moving on to, so and then what happens to both these coils, as can be seen, is that they come to a junction and they go to the neutral. Okay, they come to a junction and thereafter go to the neutral. Okay, so as for coil C, here again we are having the coil going upward over the core, though it is placed in a vertical and a horizontal sense with respect to each other. It's all happening inside the core. The flux is happening inside the core, and so the core is continuous. So we don't need to take the directional sense of the physical structure of the core. Okay, so what do we see here? We see that the current is now moving through the coil if it is allowed to flow. Okay, and then it creates a flux such that the flux now aids the flux as created by B. So B and C fluxes are in the same direction and A opposes it. Okay, so now we are having what is called as a third, perhaps a secondary coil. Okay, it's given as X, and it has and 2 is written over it. Okay, and the directional sense is not very clear. Okay, so it doesn't matter because there is a voltage, and the direction of the voltage is actually created. Not only the direction, but the magnitude of the voltage is also created as a result of the alternating flux created in the core by virtue of the three coils acting together. So now what is asked is winding A, B, and C have 20 turns each. And, okay, so 20 turns, okay, and are wound on the same iron core as shown, along with winding X, which has 2 turns. So it's a 20:2 kind of ratio for each of these coils. Okay. Figure shows the same clockwise. The figure shows the same sense clockwise or anti-clockwise of each of the windings only, and does not reflect the exact number of turns. Okay, of course, they can't show 20 turns. Okay. The windings A, B, and C are supplied with a balanced 3-phase voltage at 50 Hertz, and there is no core saturation. Of course, core saturation will completely change the picture. Okay, the no load RMS voltage in so the given voltages are RMS, not just RMS values. They are also So let's they have the voltages across their phase voltages, because each of these coils are connected across the phase and the neutral. Okay? So two aspects. Okay. No load RMS voltage in volts rounded off to 2 decimal places across winding X. Okay. So how do we proceed? Okay, of course we need to have an understanding as to what is happening there. Okay, so what is happening is that we are having VAN, VBN, and VCN. Okay, so we see that when you talk about the voltages, okay, so VBN as also VCN are reflected, because with respect to A, these the voltages created by B and C are in opposite direction. Why? Because the flux is opposed. Okay, so now we have VBN and VCN and VAN in the first and the fourth quadrant. Okay, after reflection as shown in the vector diagram. Okay, so what does it mean? Now it means that all the voltages now are added together and creating a flux such that this flux will now interact with coil X and create a voltage there based on the turns ratio. Okay, so what we have here, we have 230 volt, of course. Okay, 230 volt is now divided into a ratio of 2 by 20 because each of these points are taken into consideration. So 230 into 2 by 20, okay, and cos 60 because VBN and VCN create fluxes in the same direction as AN only in the horizontal component. The vertical components cancel each other. Okay, so the voltages are shown. It's all flux picture that we are talking about. Okay, so cos 60 is there. Of course, when you reflect back, it's 60 degrees. There's no doubt about it. Okay, and then the subsequent angle is going to be 0. Okay, and there are two of them. So 2 into 230 into 2 by 20 into cos 60 angle 0. Okay, that's with respect to both B and C phases. Okay, and the fluxes because of them. And then because of flux A, the EMF created is again 230 angle 0. Okay, multiplied by 2 by 20. There's only a horizontal component to consider. Okay? So when you add them together, okay, it's very simple to see that the resultant is going to be 46. Okay. So moving on to problem number 3, we are making good progress because we have banked upon all the information that we have been sharing so far. Okay. Again, we are having a phase, a source, EA, EB, EC. All of them are connected together at the neutral, and they supply an impedance structure, star structure, with impedances ZA, ZB, and ZC. Okay, and what is asked? Let's see. The circuit shown below, a 3-phase star connected unbalanced load is connected to a balanced 3-phase supply of 100 root 3. Okay, again. The phase to neutral voltages are now going to be equal to 100 root 3 by root 3. Okay, as usual, the voltage that is given is line to line, so we have to compute the phase voltage. And in examinations like gate, root 3, etc. is given such that now we know that the phase voltage is 100. Okay, with phase sequence ABC, there also it is conventional. The star connected load has ZA equal to 10 ohms. ZB is equal to 20 angle 60. The value of ZC in ohms for which the voltage difference between the nodes N and N dash is 0. Okay, this is a very interesting concept because if there is a voltage difference between N and N dash, then you say that there's an offset voltage, and so the voltages across each of these components, the total voltage will be EA minus the voltage across N dash. So you will have difference of voltages. Okay, this creates problems. Okay, these things. That's the reason why the neutral, okay, the neutral which is connected to the ground at your homes needs to be at 0 potential as much as possible. Okay, so now we can see that what is creating the difference. Okay, of course, the 10 ohm ZA equal to 10 ohm does not have any phase angle with respect to it, because especially because it is 100 root 3 divided by root 3 divided by ZA is going to create the current flowing in the A phase. Moving on to the other two contexts. Okay, of course, we see that we have ZB is equal to 20 angle 60, and its complement will always be 20 angle minus 60. Okay, as we saw in the earlier problem. So when they act together, it's very clear that, okay, of course, as the whole thing was mentioned in the earlier problem, it is clear that you can have the vertical components or the imaginary components cancel off, and the horizontal component of 10 ohms creating a current as given by 10 amps is now cancelled off as a result of 2 of the 20 ohms working together, one at an angle plus 60 degrees, the other then should be at an angle minus 60 degrees, just as we saw earlier, as also reflected in the problem in the vector diagram or the phasor diagram shown alongside. Okay. Moving on to the fourth problem. Okay, here we are having again the source, a 3-phase source. Of course, with the neutral and the neutral and the star point connected together. Okay, and the load connected in star just as before, but the impedances are equal this time. Okay, and what is asked is if for the balanced star connected 3-phase circuit shown in the figure, both are star, both the source as also. Okay, and moreover the neutrals are connected. Okay. The line to line voltage is 208 volt RMS. Okay, so when you're given a figure like this, okay, try to find out the phase voltage immediately because it might be useful. Okay, so 208 is not a good value. So, or in other words, it's a good value because if you divide it by root 3 to get the phase value, you will see that it's equal to 120 volt. Okay, and it is written out as point number 2 there. Per phase voltage is now equal to 120 volt. Why are we interested in this 120 volt? Because the total power absorbed by the load is 432. If each of the if all the entire load absorbs 432 watts in a balanced system, each of the loads will absorb 432 by 3, which is equal to 144 watt. Okay? Now there's a connection between 120 volt and 144. This is why I thought that you should think in terms of the numerical values given as well, because it will lead you to the problem directly. And the power factor is given as equal to 0.6 leading. Okay, and what is asked is the approximate value of the impedance Z. Okay? As usual, there are 4 different answers. So either B or C would be more correct because they have the same numerical value, but the angles are different. Okay, so now how do we proceed? We have already computed the per phase power as 144 watt. We have also computed the per phase voltage as 120 volt. Okay, so we can easily find out the current as equal to 144 divided by 120 into 0.6, because 0.6 is already given as the power factor. This is only one way of progressing. There are plenty of ways. Okay, so now we see that 2 amps is the current. Okay, and I square R, or 2 into 2 into R, will give you what is called as 144. Okay, so R is now 36, and the 36 is the horizontal component, or Z cos phi. Okay? So Z cos phi tells us that. So if that is the case, then 60 is going to be the amplitude, because 60 into 0.6 gives us 36. Okay, and it is lead power factor. Okay, so of the two versions, you can directly go for minus 53.1. Otherwise, also we have to remember that there are two important angles in our understanding. One is, of course, 53.1. The other is 36.9, somewhere near that. Okay? If 36.9 is given, then the cosine value or cos or power factor value will be equal to cos of a smaller value, so 0.8. Okay, and the reactive component will be 0.6 times. Okay, in this case, because the angle is larger, the cosine value or the power factor value is going to be 0.6, and the reactive component or whatever is associated with that will become 0.8 of the total impedance. Okay, so that's it, and then we move on to some single phase circuits, a little different with respect to each other, but still let's complete them. Fifth problem: the following circuit under steady state, we have a DC source, okay, and an AC source, but it's a series it's a series impedance, and as was discussed earlier, when there's a to DC, the capacitor is going to be an open circuit, okay, at steady state. So, and the inductor is going to be a short. Okay, so it doesn't matter, because in a series circuit, if there is an open circuit with respect to only the DC source, then the current is not going to flow. Or in other words, 5 volt DC source is immaterial. So we have a look at, so in superposition we have a look at only 10 sin t. So omega is now equal to 1. So omega L is equal to 2, and 1 by omega C is equal to 1. Okay, so j omega L minus j by omega C is going to be equal to J1. Okay, because inductor is predominant. Okay, moreover, the resistive value is also 1 ohm. So what do we have here? So the total impedance is always going to be root 2. These kinds of problems are recurring. Okay, so it's going to be root 2, and so if so if the following circuit, if 10 is given as the voltage, the current will be given by 10 by root 2. Okay, of course it will be the sinusoidal content and the maximum value. So, and that is what is asked. So 7.07 is okay, and sine, there's no change in phase, so sine is also okay. T minus 45 degrees. Why 45 degrees? Because the impedance has two components. One is the resistor, which is equal to 1 ohm, and the reactance is also J1, is also 1 ohm. So definitely the angle is going to be 45 degrees, and it is lagging. Why? Because the inductive reactance is predominant, which is 2, whereas the capacitive reactance is only minus J1. Okay. So moving on to problem number 6. What do we have here? We have we have a voltage source Vs, of course with the vectorial sense, and then there is 17.32 as the impedance, as the resistance, and the reactance is going to be 10 J10. Okay, so 10 and 17.32 are connected together. Okay, moreover, we need to find out what is called as the what is the voltage across. The angle of the angle with respect to Vs. Okay, the angle of VL with respect to Vs. Okay, so what is now? It's just a simple potential divider, and the potential divider will have Vs multiplied by J10 divided by J10 plus 17.32. So it is obvious that J10 is going to be contributing an angle equal to 90 degrees, and in the denominator you have J10 plus 17.32. So if you take out 10, it's very clear that it's going to be, yeah, you can take out 10 by 2. Okay, so then yeah, you can take out you can take out 10, then you will have 1 plus 1.732. So you take out another 2 as well, so it becomes half plus j half plus j root 3 by 2 plus j by 2. So that obviously it is half and root 3 by 2 contributing an angle 30 degrees, okay, in the denominator, and that's positive. Why? Because it's an inductor. So the positive 30 angles, when 30 degrees, when it comes to numerator, it becomes 90 minus 30 or 60 degrees. A very simple problem, and you can do it without writing out anything, so long as you understand that there is a potential divider here and the relationship between J10 and 17.3, okay, because they form the total impedance. Okay, I hope it's followed. So let's move on to problem number 7. In problem 7, the working out is not shown because you can easily work it out. Okay, so how do you proceed? Okay, you can always write, because it's a sinusoidal source. You can always replace the inductance and the capacitance by their impedance values. That is J4 omega and minus 1 by j omega, and minus 1 or minus j by omega. C is equal to 1, and then you can take the parallel combination. Okay, and finally, once you have the combination, set the imaginary values equal to 0, because that's the time when you are having resonance, because resonance is going to give you what is called as only a resistive content inside. Okay, so don't worry about 10 ohms at all. Just take the parallel combination of 4j minus j 4j omega minus j by omega in parallel to minus j by omega. Okay, so you get a particular impedance. Okay, and in the numerator, of course, you have to resolve the denominator such that it does not have any negative, any imaginary content, and then in the numerator you set the value where the imaginary content is equal to 0. So you get a value of we see that omega is now equal to 0.5 radians per second. Perhaps you'll have to work out. Okay? Yeah, but the last problem in this session is again a series RLC circuit as R equal to 50 ohms, L is equal to 100 microhenry, and C is equal to 1 microfarad. The lower half power frequency of the circuit. Okay? So there are two important aspects that need to be remembered. One is, of course, there's a formula which I'm not going to relate right now. Okay, it's better to go without a formula. For one thing, you can find out the resonance frequency, and you can also see that there is an impedance associated with half power frequency. Okay, so it is worked out. You can see that. You can read it through, and at the same time you can also realize that some kind of guesswork is good, because you can see that the resonance frequency is given by 1 by root LC, which is working out to be 10 kilohertz, 100 kilohertz. Okay, so if that is so, then the lower half power frequency has to be near around 30.5 kilohertz. Okay, so in that sense you can select the answer, or else you can read through whatever is done here. Now you can, there's another way that you can do the problem. You can say that R by L is going to be the bandwidth, okay, and the central frequency, which is the resonant frequency, will be the geometric mean of the two. Okay? So you can actually substitute and find out. Okay, the third method of doing this problem is to see that to find out the impedance at half power frequency. The question is half power frequency. At that time, we can see that we can compute the current as having an impedance component also, because when resonance happens, the impedance is only pure resistance, which is equal to 50 ohms. Okay, so if you want to find out half power, which is I square related, in that case it's going to be V by, that is the impedance is going to be the impedance, the current will be given by V square, and the current will be given by V by square root of R square plus omega L whole square or X square. There since power is proportional to I square, then it's the same, is equal to V square divided by R square plus omega square L square, okay, or X square, okay, and then you can calculate the value of the total impedance, and then you can see whether the reactive component will be given by omega L minus 1 by omega c. Okay, so in all three methods you can see that you will arrive at the same answer, which is equal to 30.55 kilohertz. Okay, so I'm not relating it completely such that we can save some time in this. You can read through the answer. Okay, thank you.